We continue with some common problems and fixes in fitting linear regression. Outliers could affect the regression value as demonstrated by Anscombe. So, an outlier is a point that has a yi value that is very far from its predicted value. One way to visualize outliers is to plot residuals, or better yet standardized residuals against predicted values. They could occur because of incorrect data recording or because the phenomena could very well be nonlinear. So, do not assume that an outlier observation should be removed. It may signal a model deficiency, example a missing predictor. A fifth potential problem with linear regression is points which have high leverage. We saw this in Anscombe's quartet, where in regression 4 it had a large horizontal outlier, a point which is called a leverage point, which is very influential on the fitted line. In simple regression, look for observations that have a predictor value outside the normal range of observations. A point has high leverage if its deletion by itself or with a few other points causes noticeable changes in the linear regression model. With many predictors in a model, one could have an observation that is within the range of each predictor's value but still be unusual. Here is an example of that. So, we have this point at 1.5 and 1, which is within the range of x1 and x2, and both have a range of -2 to +2, and here is this point which I have shown in red, which is outside the other sets of points, and this particular point could have high leverage. Another metric that is used is called the Cook's distance, and this is used to identify influential points. This measures the difference between the regression coefficients obtained from the full data and from deleting observation I. A rule of thumb is to identify points with Ci greater than 1 as highly influential. So, how do we use the built-in functions in R to help us understand these kinds of problems? So, in R we have this plot function, and that can be used after every regression model is fitted, and it comes with 4 built-in plots, and it has the residual versus fitted that we have talked about, the normal QQ plot, and then it has 2 other plots, the scale location plot and the residuals versus leverage plot. In this example, we are using the housing data set and doing the simple regression where price is regressed on lot size, and we use the plot function in R, and we have seen the top 2 plots earlier. The bottom left plot is the spread location plot, shows if residuals are spread equally along the fitted values. Plot 4 on the bottom right is used to check if there are any influential points or points with leverage, and any point with Ci greater than 1 will be flagged if there are any here. In this particular example, plots 1, 2 and 3 indicate problems with the linear model that we have used so far. The last potential problem in fitting linear regression is multicollinearity. Multicollinearity occurs when you have multiple explanatory variables, and this could create problems in fitting regression models. So, here is this example where we are using a slightly different data set, using the auto data set, and we are going to use reg 1 and reg 2 and compare the respective coefficients for cylinders. In reg 1 we are doing simple regression, in reg 2 we are doing multiple regression. And if you notice, in reg 1 you will get a coefficient of cylinder of -3.558, and it is highly significant. In reg 2 the coefficient of cylinders is -0.26 and its p value is 0.51. So, we cannot reject the null hypothesis in reg 2. So, in reg 2 cylinder's coefficient is no longer statistically significant. So, what could be the reason for this? This could indicate the presence of multicollinearity in reg 2. in the model Reg2. So, multicollinearity is when you have two or more of the explanatory variables more or less linearly related. To detect multicollinearity, one approach is to use VIF, or variance inflation factors. So, how do you get to VIFs? So, what you do is regress a predictor variable xj against all other predictor variables and name the resulting r squared as rj squared, and then define VIF for that j as 1 over 1 minus rj squared, and you do this for each one of the predictor variables. If xj has a strong relationship to the other x variables, then rj squared is close to 1 and VIF for j will be large. The rule of thumb that we use is if VIF is greater than j, then we have presence of multicollinearity. Variance inflation factors, we use the VIF function in R on the predictors of the Reg2 model and obtain these values. For cylinders, displacement and weight, we get 10.5, 15.8 and 7.8. These high VIF values indicate multicollinearity problems. And we can see potential problems from the correlation plots. If you notice, for these three variables, the correlation coefficients are 0.95, 0.898 and 0.933. So, consequences of multicollinearity in regression. If you have multicollinearity, that is if the VIF is greater than 5 as a rule of thumb, you could have several consequences. One is ordinary least squares estimated parameters may have large variances and covariances, thus making precision estimation difficult. The confidence intervals of the parameters tend to be bigger, hence we may not be able to reject the null hypothesis. The regression coefficients may have the wrong sign, or the regression coefficients may not be significantly different from 0, though r squared is high. So, adding an explanatory variable may change other variables' coefficients. So, consequences of multicollinearity, what can we do about it? So, one solution is to pick one variable if two or more measure the same thing, or use some other techniques like principal components analysis or factor analysis to create more useful variables that you could use in your linear regression model. So, recapping what we have studied in this module, we have seen how one could do visual exploration before doing regression. We have seen the importance of Anscombe's quartet, and then we have had a quick look at the assumptions of linear models, and then we looked at the common problems and fixes in fitting linear regression. We have seen these 6 common problems and what one could do to address these particular problems. Thank you.